This is losing state. Losing state. 5 can go to 2. It's a winning state.
It's a winning state.
It's going to go to 2. Winning state. 7. See, you have 4 like this. It's a losing state. You can't generalize this that easily. So in general, a common problem you'd see is they'll give you a stack of coins. Let's say they'll give you a stack n coins, and they'll give you a set of moves. It could be 1, 5, 7, 11. A random set of moves. And they'll ask you to find who wins the game for n coins. You can do this. So, simple pseudo code. Okay, how would you code this? How would you code this?
Then it will be an array.
Okay.
And then the states will be called to a vector.
Okay.
And then for 0 will be always the losing state. And then for every vector number, we'll have them as a winning state. And then generalize them.
You start from 0 to thing.
Perfect.
In OFN you can create an array. So I'll just so one for loop. So first I'll have an array. Okay, I'll keep 0 as losing state, 1 as winning state. Initially, what do? I'll set s of 0 equal to 0. Because 0 is always a losing state. Then one for loop from I equal to 1 to n. Then one other loop for all the moves. For each I, you should check all the moves. Check if all are winning states. If only if all are winning states, set it as a losing state. Otherwise, set it as a winning state. So, this thing is a golden rule. These two, very important. Most of the problems can be reduced to this one rule. So, shall we see a problem regarding this, or we'll move on? Okay, we'll come back afterwards for problems. That's fine. Okay. So, there are some famous games that are studied extensively. They're solved, you can say. So, one such game is something called NIM. NIM is a game where the players, same thing, A, B, A starts. We have n stacks, not one stack, n stacks. Each stack has a height A of I. So the stacks are not equally tall initially. It could be something like one stack has 3 coins, the other one has 2, the other one has 5, another one has 1. This could be a scenario. So here your stacks are 3, 2, 5, 1, n is 4 obviously. This could be a scenario. And the moves are, in each turn, a player can take any number of coins from any stack. Any number of coins provided it's within the stack size. But he has to take a non-zero number of coins from only one stack. He cannot take from 2 stacks. He has to take from only one stack. If a player cannot take a coin from any stack, that is, if all the stacks are empty, that player loses. Okay, so let's start off with simple. There are 2 stacks. Can you tell me who wins? A starts. It's a simple thing. Work it out. Evens. So I'll work it out. So let's say A, in the first move, he takes the full thing. If he takes a full thing, you have 0 here, and the other one has 2. B can take off these 2 evens. You understand? If A takes off the full thing in one stack, B will take off the full thing in the next stack, evens. If A takes off only 1, B will take 1 here. Then A will take, he has to take 1, it will become 0, 1. B wins. These are the possible set of moves. If it was 2, 1, now how does this change? Evens. Why?
You will take only one from the first stack.
If A takes only 1 from this stack, B will have to take 1 from this stack. A wins. A will always win this if he plays optimally. So, the theory with NIM is, the solution is, if the XOR of all these A of I, if the XOR is non-zero, A wins. If the XOR is 0, B wins. Can you understand why? It's not trivial. So let's define the trivial losing state. If everything is 0, XOR of all zeros is 0. So, correct. This is your trivial losing state. If one thing is, let's say, 5, the XOR is 5, correct? A will win because you can take off the 5. So, I'm going to give you a rough idea as to why this works. This XOR of everything is 0. So, again, it depends on that earlier rule that a state, if it can go to only winning states, it's a losing state. And if a state can go to at least one losing state, it's a winning state. So let's say we have some A0 XOR A1. Okay. This is a losing state. So what's the definition for a losing state according to the rule? Everything goes to a winning state. So what is the move in the game? What move can I make? I can reduce any one number by any amount. Correct? So if I were to reduce any number, this will obviously become non-zero. Do you understand why? If I were to reduce any number, this will become non-zero. Is everyone following this? If I were to just do a -1 here, it will become non-zero. Do you want an example for this I to become non-zero? Okay, that earlier one. 3. Okay, I'll just do 3, 2, 5. So the XOR of this is 1. Correct. Okay. So this is a winning state. Okay, this is a winning state. I'll make it 7, 0. So if I were to make any change anywhere, say I reduce 7 by 1, it becomes non-zero. I cannot do anything to make this 0 again. Any change I make here will make this non-zero. You all understand this, right? Okay. So this is the losing state. In the winning state, this case, the definition for winning state was there exists at least one move that will send it to a losing state. Correct? So there exists one move you can make such that you can make this 0, this XOR 0. So I'll give you a 3 to 5 example. 3, 2, 5. The XOR of this is, if I were to reduce the fifth one by 4, if I make it 0, 0, 1, there will always be one move that will make this array's XOR 0. Do you understand that? So let's recap. In NIM you're given n stacks. Each stack has A of I coins. In one move you can remove any number of coins from a stack, but a non-zero number, a positive number of coins, you can remove from only one stack. If A starts, A wins if the XOR of all A of I is non-zero. B wins against if the XOR is 0. You all understood why? Did you all understand why? All. Anyone want to repeat? Which one? The rule. So you're given, it's basically, let's take it as an array. So if I have 3, 1, 4, that means there are 3 stacks. The first stack has 3 coins. The second stack has 1 coin. The fourth stack has 4 coins. In one move, a player can remove any number of coins from one stack only. So he can remove all the 4 coins here, or he can remove 3 coins here, he can remove 2 coins here, or he can remove 1 coin here. Make it 0. If there are no coins left, that player whose turn it is loses. A wins if and only if the XOR of all the stack heights, 3 XOR 1 XOR 4, if this is 0, if this is non-zero, only A wins. If it is 0, B wins. Did you understand why based on that winning state, losing state?
Yeah.
So most of the questions in game theory in contest you'll see will be based on this game. Most of them. So we'll just take one sample problem. Okay. The question itself is called game theory on Keshav. So the question states that you're given 2 things as input. The player whose turn is first, A or B, whose turn it is first, and they give you a string. In one move, A can remove a certain number of alphabets of the same kind. So if I give you A, B, C, A, B. In one move, A can remove 2 A's, or he can remove 1 A, he can remove 2 B's, 1 B, or he can remove 1 C. The player who can't remove anything loses. Can you tell me how do you approach this?
Each and every algorithm
So that as a step.
All of you understood how you approach this? All. So basically you make one frequency table of everything. So you have 2 under A, 2 under B, 1 under C, XOR everything. So yeah. In this case B will always win if A starts, A will always win if B starts. You understand? If we make this the same as the earlier problem. So you all understood how nim works, right? Move on. Okay. So I'll give you an example of a game. This is not based on nim. We're gonna learn this now. We're gonna. Okay. So the game is something called floor div. Okay. Floor division game. It's from Snackdown. If you guys have done Snackdown this year, you might have encountered it. So the game starts like you have n numbers, a of I each. In each turn, you can divide a number, integer division, by 2 or 3 or 4 or 5 or 6. The person who can't divide a number further, if everything is 0, loses. Again, same thing, A starts, B's turn, so on. Each turn you can divide a number by 2 or 3 or 4 or 5 or 6. How do you approach this? Think of the first winning state. Huh?
You write the number 0 stack of these
Okay, wait, I'll simplify this first. Leave n numbers, there's only one number. A. There's only one number.
N mod 6 is 0.
Mod 6 is 0.
We will consider states A by 2, A by 2, A by 2, A by 2 states.
Okay.
0 will be a losing state initially, and then 1 is a winning state because 1 by 2 is 0 in the addition, so it goes from a winning state to a losing state, so 1 is a winning state. And then we come for 2. 2 is also again a winning state because we can divide 2 by 5, 6. And then you get a 0. Similarly for up to 6. And then from coming on 7, we will divide the number 7 by 2 or 3 or 4 or 5 or 6 and check whether they are going to a losing state.
You all understood that?
6 is a losing state.
Huh? 6 is a winning state. 6 is a winning state. 6 divided by 6 is 1.
1 by 2, so the other person will
Yeah, no matter what happens in 6, the other person wins. So you all understood that. So again, like the first thing, we can draw the state table. So 0 is a losing state, 1 is a 2 is winning state because you can divide by 3. 4 is a 3 is a winning state because you can divide by 4, it will be 0. 5 is a 4, 5, 6. Winning state, losing state. Why is 6 a losing state? Because if the greatest number you divide by 6 will take you to 1, which is a winning state. The smallest 2 will take you to 3, which is also a winning state. So you can only go to these 3 states, all are winning states. So it's a losing state. Similarly, you can find for 7, 8, 9, 10, so on. You can find for each thing. Like you said earlier, you can use one table. Let's just say one DP table we can keep for each state. DP is just a fancy name for it. Don't get tensed or anything. One 1D table which will store the state. So DP of I will tell if it's a winning state or losing state. This is how you're going to approach it if it is one stack. But now we have n stacks. Correct? We have n stacks. So how will you approach this?
So if the column contains any one winning state, then should be considered as a winning state?
No, he can remove from one column or he can remove from another column any choices. The choices is, so if it's 1, 1, 4, 5. The first fellow can remove from 4. He can make it 2 or 1 or 0. He can make 5, 2 or 1 or 0. That's his moves. He can do any of those. So you're saying is he can make 1, 0 first.
I was saying that. So to be considered as a winning state, then all the columns in the previous, all the columns should lead to.
All the columns should be winning states.
Right.
Okay.
Or either one of them, if one of the columns is a losing state, then the
Okay.
state itself.
4 and 5 both are winning states, correct? 4 is a winning state, 5 is a winning state. Correct. Both are winning states. But 4 and 5 together is a losing state.
There should be odd number of winning states.
Odd number of winning states. A is
Okay, for this thing, yeah, maybe.
No, as in there are odd number of winning states. The A is definitive to win because say A finishes the first stack by division. B will start
A
so
wins
B will
the first stack.
B
So
will
B will start the second
So he will end up in a winning state. Next A has to start. So when there is an odd number of
See, if there are 2 winning states and 1 losing state,
Yes.
see, firstly, your assumption is they finish one column, then only move to the next column. That is an assumption you're making for that.
the XOR of all these, if it's a winning state, then
XOR, yeah, okay, but like nim. But XOR of this is non-zero.
not non-zero. Then you just the XOR is a winning state or losing state. Like, you bring it to a single number and
Okay, the XOR of this is 1.
one.
1 is a winning state, but 4, 5 is a losing state.
Yeah, the XOR is the winning state must be a losing state and
4, 5 is a losing state. Wait, I'm not sure of that, but
yeah, something one by something.
okay, anyway, it's not that easy to generalize this. So we use another term called Grundy number. Have you heard of Grundy number? Okay, so use a term called Grundy number. So for each state, the Grundy number of, so let's I'll rub this off. So let's say I have a state S. S can, by some move, S can go to S0, S1, S2, Si. Okay. These are a valid state of moves from state S. I can go to S0, S1, S2. Doesn't have to be in sequence. Some states you can go to. So Grundy number of S, G of okay, this is not an actual thing. G of S I'm just using so that you can understand it easier. It's actually alright, Grundy number of S actually. So G of S is the smallest non-negative integer which does not belong to G of S0, G of S1, okay. So I'll repeat this again. So we find the Grundy number of all these states, the states that S can lead to, and G of S is the smallest non-negative integer which is not in these states. So for example, if I have a state S and the Grundy number of the states it can go to is 0, 1, 3 and 4. What is Grundy number of S? This 2. Do you understand? It's the smallest non-negative integer that does not belong in this. So G of S is 2. Everyone understand why G of S is 2? Okay. So S is a state. You can go to 4 other states from S. Let's just assume there's a state S and you can go to 4 other states. You've already calculated the Grundy number of the other states as 0, 1, 3 and 4. Okay. The other states Grundy number is 0, 1, 3 and 4. G of S is defined as the smallest non-negative integer which does not belong in this. Are you following? The smallest non-negative integer. So 2 is missing here.
Okay.
So G of S is 2. So in general, if G of S is 0, It's a losing state. Okay, so let's take that 1, 3, 4 problem. Okay, one or two problem. Come back to that 1 or 2 problem. I have a stack of coins, n coins. I have a stack of coins, n coins. I can remove 1 or 2 coins in each turn. So let's compute the Grundy number for each state. So for 0, what's the Grundy number? 0, because we're losing 2. 1. 1. 2. Everyone understanding why 2's Grundy number is 2? So from 2, you can go to these 2 states. Okay. So the smallest non-negative integer amongst the Grundy numbers of the states it can go to is 2. Because it can go to 0, it can go to 1. Now 3.
It's 2. 0.
0. Are you understanding why it's 0?
What's either division by 1 or 2?
No. See, from 3, from 3 what are the states he can go to? He can go to 1 or he can go to 2. Correct? So only 1 and 2 is there. So the smallest non-negative integer which does not belong in 1 or 2. So 3 is 0. Like this also you can define the winning state, losing state. 4 it will be 1, 5 it will be 2, 6 will be 0. So everyone following this? Huh? Okay, so coming back, let's go back. Okay, so anyway, I'll just tell you the theorem here. So if you have n of these piles, say I have n piles, you can remove 1 or 2 coins from each. N piles, each pile having a of I coins. You can remove 1 or 2 piles from a single pile, 1 or 2 coins from a single pile in each turn. The winner in this is defined as Grundy number of a of 0 XOR Grundy number of a of 1 XOR dot 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 Grundy number of a of n. If this is 0, a loses. Similar to nim, the same thing, you're reducing it to Grundy numbers. Technically, nim is a specialization of this. So, you're reducing it to Grundy numbers. If this is 0, first player loses, that is B wins. If it is non-zero, A wins. Okay, is everyone understanding?
Yeah.
Same proof is very similar to nim. You can prove it by induction using that idea. So anyway, one thing you can realize is you can derive the nim thing from this. Because in nim, the nim game, g of x equal to x. In nim. Why?
Because remove 1, 2, 3 up
Yeah.
to n.
So if my game is, I can remove any number of coins from a stack. So from 1 I can go only to 0. So I can go to 1. For 2 I can go to 1 or 0. For 3 I can go to 2 or 1 or 0. Similarly. So for the nim game, g of x equal to x. We're all understanding the XOR thing also. It's the same thing as previously. So So let's come back to that Keshav problem. Floor division game. So let's look at it for one stack first. You can divide by 2, 3, 4, 5 or 6. The stack A can be divided by 2, 3, 4 or 5. 2, 3, 4, 5 or 6. So let's define the Grundy number. Oh, 0. What's the Grundy number? Everyone understand? You all understand why it's 0, right? Losing state is 0. 1. 1 because 1 can go to 0. 2. 3 is 2. 3 cannot go to 2. You cannot divide 3 by any of these things which will go to 2. 3 can only go, if you divide 3 by 3,